In today's data-driven world, where vast amounts of information are generated every second, extracting valuable insights has become crucial for businesses and organizations. So these traditional methods often fall short when dealing with large data sets, which lead to longer processing time, increased cost, and decreased efficiency. And that is why the latest trend in AI research focus on developing novel techniques that can tackle these challenges head on. And one such breakthrough is gated sparse autoencoder, which is a cutting edge advancement in deep learning that promises to transform the landscape of next generation AI. So today we will understand this inner working of gated sparse autoencoders. We'll highlight their distinctive characteristics and showcase the practical use cases. So what exactly is this gated sparse autoencoder? In simple terms, a gated sparse autoencoder is like a filter that allows certain important features in an image or data to pass through while blocking less crucial one. So let us say you want to compress an image into a smaller size using an autoencoder network. However, since most images contain lot of unnecessary details, you don't want all information in the original image to carry over to the compressed version. So instead you want to keep only the essential parts intact so that when you expand the compressed image again, it closely resembles the original one. And that is where this gated sparse autoencoder come in handy. That is, they help select the relevant features based on their importance. And this gated sparse autoencoder consists of several stages: input, encoding, decoding, and then output. So during encoding, the first stage is called gating. So at this point, each pixel in the image goes through a gate which decide whether it passes through or not based on its significance. So if the gate deems a pixel as significant, it let it pass through unchanged. But if pixel is not critical, then the gate applies a transformation like squashing or cutting off to make sure it does not contribute much to the compression process. And after passing through the gates, the remaining pixel go through a second encoding stage, which is called magnetization. So where they actually assign the strength value indicating how strongly they affect the reconstructed image. And finally, in the last stage of decoding, these magnetized values are combined to form the compressed version of image. So when expanding the compressed image back to original size, the gates now work in reverse order to restore the suppressed pixel to their former glory. So in essence, this gated sparse autoencoder enables us to preserve the vital elements of an image while reducing noise and redundancy simultaneously. So but why we use this gated sparse autoencoder? So basically, this gated sparse autoencoder aim to address the issue of shrinkage caused by L1 penalty in the traditional stacked autoencoders through separating the roles of feature activation and magnitude estimation. And by doing so, they minimize the impact of L1 penalty on parameter estimation related to feature magnitude estimation, reducing the unwanted bias introduced by the penalty. And this approach allows for more accurate feature magnitude estimation while still maintaining sparsity in the representation learned by the stacked autoencoder. Now, what are the differences between autoencoder, sparse autoencoder, and gated sparse autoencoder? So let's understand this in simple words. Like first we'll understand autoencoder. So this autoencoder learns to compress an input into a lower dimensional space and then decompress it back to the original shape without losing too much information. So it can be thought of as a mechanism to extract meaningful pattern from raw data. For instance, consider compressing a high resolution picture of landscape into low resolution format suitable for display on your phone screen. So this autoencoder would identify and retain the essential features required to recreate the scene accurately, which will eliminate any unnecessary data along the way. Next comes the sparse autoencoder. So while this autoencoder aims to minimize the difference between the input and output signals, sparse autoencoder encourages the learning algorithms to discover minimal sets of active units instead of trying to maintain all inputs. So thus this stacked autoencoder will force the model to suppress some components of input signal that are not necessary, making it perfect for removing irrelevant noise. So consider the scenario where you need to analyze medical imagery containing numerous tiny details that could potentially obscure critical findings. So here the stacked autoencoder would prove helpful because they can discard insignificant sections highlighting the imperative portions. And finally comes this gated sparse autoencoder, which introduces a new component known as gates, which allow or disallow specific input units passed on their perceived relevance. And each unit receives a score computed via sigmoidal function applied to its input vector. So higher the score, the more likely the unit will pass after encoding. And unimportant nodes receive scores close to 0, resulting in their removal. So afterward, the remaining features proceed to magnetization, amplifying or dampening their intensity according to their contribution to the output. So in practice, these gated sparse autoencoders can enhance data efficiency, which help reduce storage requirements, and think about analyzing a vast volume of financial transactions. So here this gated sparse autoencoder may assist in identifying unusual activities faster, thereby enabling quicker response time. So what's the architecture of this gated sparse autoencoder? So basically it involves replacing the single layer value encoder in a regular sparse autoencoder with a modified version, which is called gated encoder. And this new encoder consists of three parts: gate, magnitude, and activation function. So firstly, this gate function, denoted as F gate, it will decide whether a particular input feature is considered relevant or not, and its output is passed through Heaviside step function to produce either 1 or 0. And this process ensures that this gated sparse autoencoder reduces the complexity of input by keeping only the most crucial aspect. Then comes this magnitude function, which calculates the importance level of each activated features. So here this input vector undergoes another transformation and it results a scale down if deemed less significant compared to others. And these magnitudes helps the decoding stage reconstruct the input more precisely, since crucial information has more influence over the final results. And lastly, the activation function, which is represented by ReLU, perform nonlinear transformations on selected feature vectors to produce the output. So to summarize this, we can say this gated sparse autoencoder employs gates and magnitudes to selectively preserve key characteristics during encoding, enhancing overall performance while minimizing computational overhead due to shared weights between the gates and magnitude function. And by doing so, this gated sparse autoencoder optimizes the trade-off between representation quality and resource usage. Now comes the applications of this. First application can be in image denoising. So whenever we capture pictures digitally, sometimes noise get added unintentionally due to various factors like low light condition, camera shake, etc. So here this gated sparse autoencoders can be useful because they can identify which areas of picture have actual objects versus those contaminated by noise. So using this gate mechanism, they can filter out those corrupted regions from further processing, leaving only the clean part intact. And then using the magnitude estimator, they can accurately estimate the intensity level of remaining objects. And finally, this restored output will contain sharp edges and clear textures, giving us a high quality image. Then comes the dimensionality reduction. So this gated sparse autoencoder also helpful for shrinking dataset with numerous attributes. For instance, let us say you process a vast dataset containing customer purchasing history, but some features are redundant or irrelevant. So you might want to cut back on computational time by eliminating unnecessary columns before feeding them into another machine learning algorithm. So utilizing this gate network, this gated sparse autoencoders can distinguish between necessary and useless items and can suppress the later. So with the reduced dimensions, you now can have a compact yet meaningful representation. And then comes the semantic segmentation. So here, this gated sparse autoencoders can assist in categorizing image pixel wise. For example, imagine a self-driving car navigating through the city landscape. So it needs to know which segment represent road surfaces, pedestrian, traffic signals, and buildings. So through this gate mechanism, this gated sparse autoencoders can distinguish relevant portions for each class and can eliminate the rest. Then magnitude estimator define the boundaries and shape within each categories. And these fine-grained details allow the vehicle to perceive better environment and respond accordingly. So overall, this gated sparse autoencoder contributes significantly to improve the quality, speed, and accuracy of diverse applications by managing the intricacies inherent in big data, visual computing, and multimedia processing. Thank you.